Good morning everyone. Myself Lokesh Soni and I am working as assistant professor in AKG EC Ghaziabad. So today's lecture is the continuation with the second lecture, that is binary codes. So in the last lecture I have explained the BCD codes, access3 codes, and now in this lecture I will explain how we convert binary to gray to binary, and how we can detect and correct the error using the Hamming codes. So if we want to convert any binary number into a gray code, for example, this is a binary number 11001001. This is our binary number. So how we can convert this binary into a gray code? So the method is that the MSB of the binary number should be same. This is a binary code and this is our gray code. So the MSB bits should be same, and for the next bits we have to take the XOR of the upper two bits of the binary number. So first I will explain the XOR gate. What XOR gate will do? This is A, B, and this is the output of the XOR gate, that is Y, and this is the symbol of the XOR gate. This is A, this is B, and this is the output Y. Since there is a two inputs, so four possible combination are there: 0, 0, 0, 1, 1, 0, and 1, 1. So for in XOR gate, the output will be 0 for the same inputs. As we can see here, A and B both are same for 0, 0, and 1, 1. So output will be 0. And for the different cases, the output will be 1. So if we are applying the XOR concept here, if we XOR 1, that is 0. Again for the next bit, we have to take the XOR of the upper two bits of the binary number. So 1 XOR 0 is 1 because these two are different. Again 0 XOR 0 are same bits, so 0 XOR 0 will be 0. Again 0 XOR 1, these are different, so 0 XOR 1 will be 1. 1 XOR 0, different bits, it will give 1. 0 XOR 1, again different bits, it will give 1. So this is our gray code of the given binary number. So that's how we can convert any binary number into a gray code. Just the MSB bits should be same, and for the next bits we have to take the XOR of the two upper bits of the binary numbers. Next is gray to binary. Earlier we have seen that how we convert binary to gray. Now in this case we will consider the gray code and we want to convert into a binary. So our gray code is given as 11000101. Then how we can convert into a binary? For that, the first bit should be same as in the case of binary to gray. The MSB bit should be same. So this is our MSB bit. Now for the next bits, we have to take the XOR, but in gray to binary we have to take the XOR of the previous bit of the gray binary to the next bit of the gray. That means 1 XOR 1, it will give 0. Again for the next bit we have to take the previous bit of the binary number and next bit of the gray. So 0 XOR 0 will give 0 because both are same. Again 0 XOR 0, both are same, so it will give 0. Again 0 XOR 1, both are different bits, so it will give 1. Again 1 XOR 0, these are different bits, it will give 1, and 1 XOR 1, both are same, so it will give 0. So this is our binary number obtained from the gray code. So the main difference between the binary to gray and gray to binary is that in binary to gray conversion we have to take the XOR of the binary bits, whereas in gray to binary conversion we have to take the XOR of the previous bit of the binary to the next bit of the gray code. And one advantage of the gray code is that in gray code, if we can see that there is only a 1 bit difference at each position. Like for example, if we are taking an example of binary code, in binary code, the minimum change between the bits could be 1, or all 3 bits can be changed. So in binary, the minimum bit can change up to 1, and it will go up to 3 or 4. That means all bits can be changed. But in the case of gray code, only 1 bit will change at a time. Like here we can see that from 00 to 001, only 1 bit will change. From here to here, again only 1 bit will change, 0 to 1, rest are same. From here to here, again only 1 bit is changed. From these two, again only 1 bit is changed, and again 1 bit is changed. So this is the advantage of gray code over binary code. Whereas in binary code, as we can see in that here 2 bits are changed. Here 2 bits are changed. So the gray code advantage is that there is a less number of transition between the bits. So it will consume less power as compared to a binary codes if we are using in a circuit implementation. Also, the gray code is known as the cyclic nature. What does mean? Cyclic nature means if we can take the first bit 000 and last 100, there is only a 1 bit difference. Again, if we take the second last bit 001 to the second bit, there is only a 1 bit difference. So there will be a cyclic between the 1 to last, second to second last, third to third last. So this will behave as a cyclic nature, like there is only a 1 bit change between any two consecutive numbers. Our next topic is Hamming code. Hamming code generally we are using when we are transferring some data in a communication system, and in digital communication at transmitter side or at receiver side. For example, if we are sending some message signal 11010001, and if due to some environmental variation or some circuit defects, if there is some error, then how we can detect and correct that error, and how we can detect that at which place the error will happen. So, and due to this error, our bit will get changed. For example, earlier our message was 110, but due to an error, it will change to 101. That means these two bits will be changed due to an error. Then how we can find out at the receiver side that these two bits are changed? Because at receiver side, we don't know what signal is transmitted at the transmitter side. So for that, we are using the Hamming code. Hamming code is used for detect and correct the error. Second point is, it uses the concept of parity bits. That means if we want to detect or correct the error, we have to add some parity bits in the codes, transmitted code. So these parity bits are help to detect the error at that particular places. So how we can detect and correct the error? Let's say we are taking this example only 11010001. Here if we can see that number of bits are 7. 1, 2, 3, 4, 5, 6, 7. There are 7 bits are in the transmitted signal. And the parity bits are added by using this formula. 2 to the power p greater than equal to m plus p plus 1. Where we have to find out the minimum value of p. P is the parity bits. That means how many parity bits we have to add in the particular transmitted signal. That we have to find out from this formula. For example, 2 to the power of p should be greater than or equal to, here number of bits are 7. So the value of m is 7. 7 plus p plus 1. Here m is 7 because number of bits are 7. So if we can solve this, 2 to the power of p should be greater than or equal to 8 plus p. So what should be the minimum value of P that will satisfy this equation? So P should be P equal to 4 because 2 to the power of 4 greater than 8 plus 4, that is 12. So the minimum value of P in this particular code should be 4. So we have taken the P equal to 4. So now if we add 4 parity bits in a transmitted signal, so total number of bits becomes 7 plus 4, that is 11. In step 2, now we have find out the number of parity bits we have to, how many parity bits we have to add in a signal. Then how we can find out the location of these parity bits? For that, the parity bits are generally added in the power of 2. That is 2 to the power of 0, 2 to the power 1, 2 to the power of 2, 2 to the power of 3 and so on. Since we have to add 4 parity bits, so we take 2 to the power of 0, that means at 1th place the first parity bit should be added. 2 to the power of 1, that is 2, so at the second place P2 will be added. 2 to the power of 2 is 4, so at the 4th place third parity bit should be added, and 2 to the power of 3 is 8, that is 4th parity bit should be added at the place of 8. Now how we can find out the value of these parity bits? As we can observe that by adding these 4 parity bits, our message signal will become 11 bits long. 7 plus 4 are parity bits. So in step 2, we have to we have to find out the location of the parity bits. If we have to add 5 parity bits, then it will go up to 2 to the power of 4, 2 to the power of 5 and so on, if our message is long at that enough. So now how we can calculate the value of the parity bits? For example, for P1, first we have to find out the value of the P1. For P1, we have to take the XOR of the conjugative bits. Since P1 is the 1th place, so we will take the bits by skipping the one value in between them. For example, if for P1 we will take 1, 3, 5, 7, 9 and 11. P1 we will skip one bit in between them and XOR the bit positions. For example, at 1 P1 is already exist, but at 3 we have 1, we have 1 at the third place, and at 5 we have again 1, at 7 we have 1, at 9 we have 0 and at 11 we have 1. So if we are using the even parity means there should be an even number of ones in a message signal. So as we can observe that there are 4 ones, that means it is already in a even parity. So P1 value should be 0 because we need not have to place one extra one because this is already in a even parity form. Again for P2, we have to take 2 bits conjugative and skip 2 bits and again take further 2 bits. So for P2, we take 2, 3 and skip 4, 5 and take 6, 7, skip 8, 9 and take 10 and 11. Again we have to note it down the bit positions. At 2 we have P2, at 3 we have 1, at 6 and 7 we have 0 and 1, 10 and 11 we have 0 and 1 again. So here we can observe that there are 3 ones, that means this is in an odd number. So for even parity, the value of 1 should be in even form. So the value of P2 should be 1. Then only this message signal will become even, because if P2 is 1, there will be a 4 ones. So that's how we have to calculate the position of the value of the parity bits. For P3, we have to take 3 bits and skip 3 bits. So for P3 we will take 4, 5, 6 and 7 and skip 8, 9, 10. So for P3, if we are having for P3 we have 4, 5, 6, that is P3. At 5 we have 1, at 6 we have 0, at 7 we have 1. So as we can observe that there are 2 ones already placed. That means this is already in a even parity form. So the value of P3 should be 0. For P4 we have to take 4 bits and skip 4 bits. So for P4, here is a P4. So we have to start taking the bits from here only. So 8, 9, 10, 11 we will take, and there is no signal further. So we have to stop it here. So 8, 9, 10, 11. At 8 we have P4. At 9 we have 0. At 10 we have 0. At 11 we have 1. So there is only one is appear. That means this is in an odd form. So to make it in an even, the P4 value should be 1. So that's why the P4 should be 1 in this case. So that's how we have to find out the value of the parity bits in a message signal. So in place of P1, P2, P3 and P4, we have to replace this parity bits by 0, 1, 0, 1. So now our message signal will become, this is our parity bit 1, this is our parity bit 2, this is our parity bit 3, and this is our parity bit 4. So now our message signal becomes 0, 1, 1, 0, 1, 0, 1, 1, 0, 0, 1. This is a 11 bit long. Now the received code is now becomes 11 bits. Then how we can find out if there is any error or not? For that, since for P1 we will take 1 bit at a time and skip 1 bit. So 1, 3, 5, 7, 9, 11 we will take in the earlier slide also. So there will be 3 odd ones. So as we can observe from here, at 1 we have 0, at 3 we have 1, at 5 we have 1, at 7 we have 0, at 9 we have 0 and at 11 we have 1. That means there is a 3 odd. That means there is an odd number of ones. So there is a conflict. This is not in a even parity form. So so the value of the P1 should be 1. So there is an error at that place. It should be a 1, not 0. Now for P2, we will take 2 bits at a time, 2, 3, 6, 7, 10, 11. We can observe from this, the 2 is 1, 3 is 1, 6 and 7 are 0 and 0, 10 and 11 are 0, 1. Again, there is an odd number of ones. So the value of P2 should be 1 in that case. So there is also an error. For P3, we will take 4, 5, 6, 7. So at 4 we have 0, 5 we have 1, 6 we have 0, 7 we have 0. Again, there is an odd number of ones. So we have to add 1 in that place also. For P4, 8, 9, 10, 11 we have to take. At 8 we have 1, 9 we have 0, 10 we have 0 and 11 we have 1. Now there is an even number of ones. That means P4 bit is correct. So there is no need to change the P4 bits. But we have to change the P1, P2 and P3 bits. So P1, P2, P3 and P4 should be as it is. So P1, P2, P3 should be 1, 1, 1 because we have to make an even parity. So these 3 bits should be 1. Whereas P4 should be 0 because this is also already in a even parity form. So it will equivalent to a 7, 0, 1, 1, 1. This is equivalent to a 7. That means there is an error at the 7th place in a bit. So what is the 7th bit in a message signal? 1, 2, 3, 4, 5, 6, 7. That means this 0. This 0 should be replaced by an 1. because this code will give us a 7. That means at the 7th place there is an error. So 1, 2, 3, 4, 5, 6, 7. Now earlier it was 0, but to correct the code we have to replace it by 1. So this is the corrected form of the transmitted signal. So that's how we will detect and correct the error in an transmitted signal by using the Hamming codes. So that's all for this today's lecture. Thank you everyone.